This is lecture 11, network models for IE 3340 operation research. In this lecture, we are going to introduce a different way of representing some linear programming models by using networks. And the idea, as you saw in the transportation model, is that there are certain type of problems in linear programming that can be represented by nodes and arcs. And those models can be solved using linear programming, the simplex method, and so on. But we can also take advantage of the structure of the problem, and we can represent those models in a graph. So the idea by representing these models using a graph is to use a structure and find ways to solve those problems easily. And that's the purpose of this lecture. So network models. So this lecture is the last lecture for this course, in which we are going to, again, use some of this knowledge that we have acquired during this semester in terms of linear programming, transportation problem, the assignment problem, and now use all that information to develop an understanding of the networks. So networks by itself is a large area of research, and you can have a single course just covering network theory and network applications. So what we are going to discuss in this lecture is an introduction. And this is part of one of the objectives for this class, to recognize, analyze, formulate, and solve industrial problems that can be dealt with linear programming. So what are the learning objectives for this lecture is to discuss special types of linear integer programming problems, specifically those that are represented using networks. And then after we learn about this network theory, we are going to talk about a specific problem within network theory, which is the shortest path problem. And we're going to learn specialized algorithms for this type of problem, how to solve this problem using an algorithm. So again, we can formulate this problem using the linear programming, and we can solve it using the simplex method. But by taking advantage of this network structure, we can design another way to solve the problem, which is faster and also provides you with an optimal solution. So that's what we are going to learn, which is the Dijkstra's algorithm. So what is the agenda for this lecture? We're going to start describing the notation and terminology for networks. Then we're going to transition to the shortest path problem. And finally, we're going to discuss how to use the Dijkstra's algorithm to solve the shortest path problem. So let's start with the notation and terminology. It's a general description. The optimizations models or network models are optimizations models that exhibit a very special structure. For special cases, this structure dramatically reduces the computational complexity, which is what we are trying to achieve when we are formulating using this strategy for formulating the problems. We want to make sure that we can solve the problem, still get the same solution, but we are getting some savings in terms of computational effort. So first, widespread application of LP to problems of industrial logistics, as I mentioned, such as the transportation problem, and addresses huge number of diverse applications. So let's talk about the notation and terminology. What we are seeing here with nodes, yellow nodes, and arcs. This is called a network. It could be also called a directed graph, a digraph, or a graph by itself. So, so the network itself, I mean, based on this example, it is named G, and the network will have two pieces, a N set, which includes the nodes, and a set, which includes the arc set. The node set in this case are 1, 2, 3, and 4. Those are the 4 nodes for this network. And the arc set are typically defined as pairs, in which you have the node that starts the arc and the node that ends the arc. So as you can see, based on the direction, we have an arc that goes from 1 to 2. We have an arc that goes from 1 to 3. We have an arc that goes from 3 to 2. We have an arc that goes from 3 to 4. And finally, we have an arc that goes from 2 to 4. There's a difference between what is called a directed and an undirected network. As you can see in these two examples, by looking at the graph, there's the only difference between them, in addition to the colors of the nodes, is that in the graph on the right, you have some arrows. So you have the direction specified by an arrow. On the left side, you just have the network with no arrows. You just have the lines connecting the nodes. So when you don't have any arrows, that's what's called an undirected graph. And when you have the arrows specifying the flow, that is what's called a directed graph. So networks are used to transport commodities like physical goods, communication, electricity, and many more applications. The field of network optimization concerns optimization problems on networks. As mentioned already, networks are everywhere. So we have physical networks, road networks, railway networks, airline traffic networks, electrical networks, and so on. What we are showing on this right side of the slide is the rail network for New York City. We also have abstract networks such as organizational charts, precedent relationships in projects, and so on. Any other type of network? Well, now we have the social networks, which is also a type of network, professional networks, and so on. So in terms of an overview, networks and graphs are powerful modeling tools. Most operation research models have networks or graphs as a major aspect. So next, we're going to discuss the representation of networks, a great insight from computer scientists. How data is represented is important to how it is used. So we're going to discuss about different ways of storing the same data, but each way of representing the data will have advantages and disadvantages based on computational complexity and what you want to achieve in terms of solution methods. So the first thing that we want to discuss is what is called the adjacency matrix for directed graphs. And in this type of representation for a network, we have a row for each node. We have a column for each node. And we put a 1 in row I, column J, if IJ is an arc. So what that means is you will have a directed graph and you only put in a 1 for those coordinates in the matrix in which you have a directed arrow pointing between these two nodes. So again, in this case, for the first row, we have 2 1s. The first one is for arc 1, 2. And the second one is for arc 1, 4. Since we don't have any other arc leaving 1, then the rest of the elements in that row are equal to 0. For the second row, we have only 1, 1. If you go to node number 2, you see that there's only one arrow pointing out of 2. So that's why we only have a 1 in that row, and that one goes from 2 to 3. We do the same exercise for node number 3. You see that number 3 has no arrows coming out of that node. So since there's no arrows coming out that node, there's no 1s in that row. So 3 has no 1s. And then finally, we have node number 4 with 2 arrows pointing from 4 to 2 and 4 to 3. So that's why we have a 1 in that in row number 4. One goes from 4 to 2, and another one goes from 4 to 3. So this is what is called an adjacency matrix, and this is a way of representing a network for example, if you were to implement this into an algorithm in a computer. You cannot present the computer with the drawing of the network, but you can give the computer or the code the representation in terms of a matrix. So what will happen if 4-2 becomes 2-4? So basically, if we switch the direction of arc 4-2 to 2 to 4, then we're gonna have to change the value for this. Where is it? So 4 to 2 will become 0, and 2 for this will become a 1. So that's to answer this question. Okay, so now for the adjacency matrix for undirected graph, we have a row for each node. We have a column for each node. We put a 1 in row I, column J, if ij is an arc. So now we're gonna have multiple, or I guess 2 1s for each arc represented in the matrix. So if you can see from 1 to 4, we have this. So if I'm looking at this arc, 1 to 4 has a 1, but also 4 to 1 has a 1. Okay, so each arc will have a representation in the matrix, and you have to represent both directions. So that will be the major difference between this one and the previous one. The degree of a node is the number of incident arcs. Okay, so we can discuss that with an example in a minute. So again, the degree of a node is the number of incident arcs. So what is the degree for each one of these nodes? We have for node number 1, we have 2. For node number 2, we have 3. The number 3, we have 2, degree number 2. And then for number 4, we have 3. The node arc incidence matrix is another way to represent directed graphs. So we're gonna have a row for each node. We're gonna have a column for each arc. So now each arc is represented by a letter. Okay, so letter A, letter B, letter C, letter D, and letter E. So each arc is represented by a letter. So in the previous 2 representations, we were not using the name of the arcs. In this one, we are. So we put a 1 in row I, column J, if arc J starts at node 1. Okay, so we put a 1 in row I, column J, if arc J starts at node I. So, so I guess, let me show you this. We put a -1 in row I, column J, if arc J ends at node I. So this is how this will look like. So if you go, for example, if you look at A, let me use another color. If I use A, then I'm looking at A. If I use A, we know that it's gonna be, since it leaves 1, node 1, then you have a +1 here. And it is a -1 on that node that is ending. So in this case, that will be here in node 4. Let's look at another one. So if I look at B, right? B starts in 1. So B starts in 1 and ends in 2. And so on. So we use -1, +1, depending on whether it ends or it starts on a specific node. So again, the question, what will happen if arc42 became arc24? So if we have something like this, so instead of having this, we have this. What will happen if that's the case? So if that's the case, then we will switch the direction of this. So 4-2, if you look at arc C, it's saying that it starts in 4 and it ends here. So what's gonna happen is you have to switch the signs. So now this is gonna be positive. I'm sorry, that's gonna be negative. So this is gonna be negative now, and this is gonna be positive if we answer this question. Representation of arc list for directed graphs. So in this other representation, we created a list arcs for each node. So we have, for node number 1, we have 2 arcs. So you can see for, we have this arc and we have this arc for 1. So 1, 2, this is this arc. And 1, 4 is this arc. Same thing for 2. We have arc 2, 3, which is this arc. For 3, we have no arcs because both of them are going in. For 4, we have 2 arcs, 4, 2, and 4, 3. So this is again another way to representing directed graphs. This is called the representation of arc list. And there are lots of very similar variants of this type of representation. So we have discussed 4 different representations as part of this lecture, but there are more than that. On network representations, each representation has its advantages. Major purpose of a representation is the efficiency in algorithms and the ease of use. Note our incidence matrix shows up in linear programs. And next, we're gonna do definitions for networks. So there's some definitions in this slide. A path is what is known, I'll always also call it a route. So basically, you have no node is repeated in that path and directions are ignored. So for instance, this could be a path for this problem. So you go from here to here, no directions and no nodes are repeated. A directed graph is, again, no node is repeated, but in this one, directions are important. So for instance, in this case, we go from 1 to 2, 2 to 5, 5 to 3, and 3 to 4. So we are following the direction of the arrows. A cycle is a path with 2 or more nodes, except that the first node is the last node. So that first node is the same as the last node. So you have to close that cycle or loop. So if you look at this could be a cycle. Again, you start with 1 and you end also in 1. A directed cycle, so in this cycle by itself, the first one that we just discussed, the directions are ignored. If you have a directed cycle, then you take into account the direction. So you see now you have these arrows, so you have to make sure that your cycle follow those arrows. So 1 to 2, 2 to 3, 3 to 4, and then back to 1. A walks are paths that can repeat nodes and arcs. An example of a directed walk is 1, 2, 1, 2, 3, 5. So 1, 2, 2 to 3, 3 to 5, 4, 5 to 4, 4 to 2, 2 to 3, and 3 to 5. So that's a directed walk. So again, in walks are the paths that can repeat nodes and arcs. So as you can see in this one, you can see that there's repetition in this side and this side. A walk is closed if its first and last node are the same. Closed walk is a cycle, except that it can repeat nodes and arcs. More terminology, an undirected network is connected if every node can be reached from every other node by a path, which is the case here. A directed network is connected if its undirected version is connected. This directed graph is connected even though there is no directed path between 2 and 5. A nice application, I mean, this is the beginning of graph theory and networks. It began in 1736. This is a nice application. It's called the bridges of Königsberg. So Leonhard Euler visited Königsberg, and people wonder whether it is possible to take a walk, end up where you started from, and cross each bridge in Königsberg exactly once. Generally, it was believed to be impossible. So these are the bridges, and so the question is it possible to start in A, cross over each bridge exactly once, and end up back in A? So you want to start here, cross each bridge only once, and then go back to A. So is it possible? So we can conceptualize this as nodes, the land masses as nodes, and then the bridges can be conceptualized as arcs. And we can develop a network. So this translation to graphs or networks. So now, is there a wall starting at A and ending at A and passing through each arc exactly once? Question is, why isn't there such a walk? So by looking at this network by itself, if you try to do this exercise by hand, you'll find out that there's no such a walk. The question is why? Why isn't there such a walk? So adding two bridges creates such a walk. And I want you to notice that the number of arcs incident to B is twice the number of times that B appears on the walk. So here's the walk. You go from A, go through 1, then go to 5, 6, 4, 8, 3, 7, 9, and 2 to go back to A. So this is what is known as the Eulerian cycle. It is a closed walk that passes through each arc exactly once. For this cycle to exist, the degree of a node has to be equal to the number of arcs incident to the node. The necessary condition is each node has an even degree. Why is this necessary? The degree of a node J is twice the number of times J appears on the walk, except for the initial and final node of the walk. If every node has even degree, and if the graph is connected, then there is a Eulerian cycle. So we need these two conditions to be satisfied in order for such a walk to exist. The Eulerian cycles and extensions are used in practice, for example, for mail carrier routes, in which the mailman will, or yes, the post office will visit each city block at least once to minimize the travel time, and maybe there be other constraints in practice. And also for trash pickup routes, in which we visit each city block at least once. We also minimize the travel time, and there are also other constraints in practice. Some additional definitions. So a network is connected even if every node can be reached from every node or every other node by following a sequence of arcs in which the directions is ignored. A spanning tree is a connected subset of a network, including all nodes, but containing no cycles. So this is what is called a spanning tree. An out tree is a spanning tree in which every node has exactly one incoming arc, except for the root. As a theorem, in an out tree, there is a directed path from the root to all other nodes. All paths come out of the root. So now let's look at one application, which is called the shortest path problem. And I have an example here. So the question is, we have a network, we have nodes and arcs, and we have a source node. In this case, that is the source node is node number 1, and we have a sink node, which is node number 6. And the question that we need to answer is, what is the shortest path from a source node, often denoted as S, to a sink node, often denoted as T? And what is the shortest path from node 1 to node 6? The assumptions for this lecture is that there's a path from the source to all other nodes and that all arcs length are non-negative. I want to make a note here. I know that if you look at this graph, by eye, you can identify the optimal solution. However, in practice, you will have a network, or you will have networks that are so big that it will be impossible for you to find the optimal solution by eye. So again, the purpose of this lecture is to show you how to apply the algorithm and the solution for this problem, and to find a solution for this problem, so you can extend that to larger problems if needed. Okay, so that being said, in the exam or in the homework, I want you to, if I ask you to solve a problem like this, I need you to use the algorithm. I just don't want you to look at the network and try to identify that by eye, because that's not the idea. The idea is that you know how the method works. So when you are faced with a problem, maybe a larger problem in which you are unable to find the solution by eye, you can apply the algorithm and you can solve the problem. Okay, so let's look at this problem. Where does this type of application arise in practice? Common applications: a shortest path in a vehicle, shortest path in internet routing, and shortest path around Texas State University. How will we solve the shortest path problem? We're going to use the Dijkstra's algorithm. So again, as I mentioned, we can find the shortest path by inspection. So if you look at the possible options here, we have 2, 4, 2 that is equal to 8. You also have 2, 2, and 2 that's equal to 6. You have 2, 1, 3, 2, which is equal to 8. And then have 4, 3, and 2, which is equal to 9. So the shortest path by inspection should be equal to 6 based on my based on what I'm seeing in this network. But again, the purpose of this is for you to be able to apply the algorithm. So when you're faced with larger problems, you can solve the problem. Because sometimes the problem will be so big that you are not going to be able to find the solution by hand or by looking just at the network. So the exercise finds the shortest path from node 1 to all other nodes. Keep track of distances using labels. So di and each node immediate predecessor I. So we're going to keep track of these two lists. We have a list di and we have a list predecessor I. So as you can see here, we are keeping track of these two lists. One here and one here. Okay, so let's look at the solution. So find the shortest path from node 1 to all other nodes. Keep track of distances using labels di and each node immediate predecessor using list predecessor I. So if we look at 1, the immediate nodes for 1 are node 2 and node 3. So we want to know, we start with distance of 1. The distance of 1 is equal to 0 because that's the source node. And the predecessor of 1 is 0 because there's no nodes coming from or coming to 1. Okay, so those two lists are empty, and that is expected because this is the first node. If we look at D2 being the node, this is node number 2. The distance 2 will be 1 to 2, that's 2. So that distance is what we have here. What is the predecessor of node number 2? The predecessor is node 1. Okay, so for us to get to 2, there's a distance of 2, and the predecessor is node number 1. Find the other distances in order of increasing distance from node 1. So a key step in the shortest path algorithm, we let D denote the vector of temporary distance labels. Dj is the length of some path from the origin node 1 to node j. So for example, here we have a path that takes you from 1 to I, and that path is distance is 62 units. If you go from I to j and there's distance of 10, then this distance is going to be updated to reflect that there's a better distance or a shortest path to j. So in this case, that will be 62 plus 10. So this is going to be equal to 72. So what is the procedure to update? This is the pseudocode. You're going to look up for each arc. You're going to check for the distance. If the distance to j is greater than the distance I plus Cij, then if that's the case, di plus Cij, so that new distance is going to be, dj is going to be equal to di plus Cij. And the predecessor will be the new node. So in this case, as I mentioned, the original distance was 78, but now we found another path from I to j in which the shortest distance is no longer 78, it's 72. So that's why we update that distance from 78 to 72. So up to this point, the best path from 1 to j has length 78, but Pij is a path from 1 to j of length 72. So that's the shortest distance. So that's why we update the current distance at j from 78 to 72. So let's look at the Dijkstra's algorithm. So again, this is the pseudocode. If you were to implement this in a computer, we have a set of distances and a set of predecessors. They're empty. We have the distance j equal to infinite for each j in this set n. And we start with the list S, which S is the source node. While the list is not equal to empty, we proceed as follows. We let the distance I equals to the minimum of the distance j for all j's in the list. We remove I from the list, we update I, and if dj decreases, we place j in list j, in the list set. So let's look at this in let's look at this example. Okay, so remember we keep a set of predecessors, we keep a set of distances, and we also keep a list. So we start with node 1. We have no predecessor because there's no other node linked to this node. So we initialize the distance and list. List is a set. So distance to 1 is equal to 0 because this is the source node. And then we initialize all the other nodes. For the purpose of this, we are going to start all the nodes with distances infinite. Okay, so this is a very large number. What we want to have is a very large number because we want to update that with smaller distances. Okay, so our list starts with 1 because that's the node that we are currently looking, source node. So the source node. And then from here, we're going to find a node I on the list. We only have 1 with the minimum distance. So 1 is the only node, so we start with 1. And from here, we scan the arcs out of I and update D and pre and the sets D and pred and list. So we can reach node number 2 from 1. And we know the distance is, 2 is better than infinite. So we update from infinite to 2. And we also update the predecessor for 2. The predecessor for 2 is now 1. Okay, and we are going to also do the same thing for the 3 because we can reach 3 from 1. So the distance from 1 to 3 is 4, so that's smaller than infinite. So we update, and then the predecessor of 3 is 1. Since we added this to, we reached to 2 and 3 from 1, we can add those 2 nodes to the list. Okay, and we are done with 1, so we can scratch that one. So now we have 2 nodes in the list. So again, we find the node I on list with the minimum distance. So we have 2 and 3. The minimum distance is distance 2. So we're going to move with 2. And then from 2, we repeat the process, which nodes we can reach from 2. So we can reach 4. So the distance from 2 to 4 is 4 plus 2. Distance from 1 to 4 is going to be equal to 6. So we can update that distance to 6, and we can update also the predecessor for 4 is 2, because 2 is the node that is connecting from 1 to 4. Okay, so we do the same thing for the next one. 5, you can also reach 5 from 2. The distance is going to be 2 plus 2, which is 4. So it's smaller than infinite. So this is going to be 4, and we're going to update the predecessor of 5 to 2. And then finally, we have from 2, we can also reach 3. If you look at the distance from 1, 2, and 2, 3 is equal to 3. That is smaller than 4. So we can update this 4 to 3. And we can also update the predecessor. It's no longer 1, the predecessor is 2, because the distance through 2 is better than the distance straight from 1. Okay, so from this point, what do we have? We have 3, 4, and 5 now part of the list, and we are done with 2. Okay, so we have 3 nodes that we have to search. Which one has the minimum distance? But the minimum distance, if you look at 3, the distance is 3. You look at 5, the distance is 4. If you look at 4, the distance is 6. So the minimum distance is for 3. So we're going to start from 3. Okay, and then we're going to scan. The only node that we can reach from 3 is 5. So scan the arcs out of I and update D and predecessor and list. So what would be the distance from 3 to 5 is 3, plus the distance from 1 to 3 is 3. So if we sum 3 plus 3, that is going to be equal to 6. 6 is larger than 4. So we are not going to update the distance of 5, because if you go through 3 up, if you go to 5 through using 3, the distance is going to be larger. So we are trying to find the shortest path. So in that case, updating is not possible, because 3, which is the distance up to 3, plus 3, which is the distance from 3 to 5, is going to be 6, and 6 is greater than 4. So in that case, we don't update, we keep 4. So we are done with 3. So we have 2 nodes in the list, 4 and 5. We're going to look for the node in the list with the minimum distance. So we have 6 and we have 4. So the minimum distance is for 5. So we're going to start with 5. From 5, you can reach 4 and you can reach 6. So if you look at 4, from 5 to 4, distance is 4 plus 3. the distance is 7. 4 plus 3 is 7. So you don't update because 7 is greater than 6. Okay, so this is not making an improvement. Going to 4 from 5 is a larger distance than going to 4 from 2. So we don't update. Okay, so in that case, we don't update. Then we look at 6, from 5 to 6, distance is infinite. Up to this point is 4, up to 5 plus 2 is equal to 6. 6 is less than infinite. So we update and we state that the predecessor for 6 is 5. So we are done with 5. We still have 4 and 6. Distance of 4 and 6 is the same. So we are gonna choose 4 arbitrarily because that's the only node that is still pending in terms of not reaching the sync node. So if we look to 4, the nodes that you can reach is only 6. Your distance is 6 at this point, plus 2 is going to be equal to 8. 8 is greater than 6, so you don't update. So you are done with 4. And now the only node that's still pending, find the list of nodes when the minimum distance is 6, but 6 is the sync node. So at that point, we're done. And we are ready to set up our solution. So this is the end. So what is the solution? Die-Trust provides the shortest path from node 1 to all other nodes. It provides the shortest path 3. Note that this 3 is an out 3. So each node has one incoming arc except for the source. So what is the solution for this problem? So to find the shortest path from node J, trace back from the node to the source. So in this case, we go from 6 to 5. So that's equal to 2. We go, I'm sorry, that's correct. So maybe if I use this, it's easier. So the optimal solution, once you have this, you start with 6. So you know that the shortest path is 6. That is the distance. But you want to know which nodes are associated with that distance. So you go to this set, the predecessors. So the predecessor of 6 is 5. So you start 6 and then 5. The predecessor of 5 is 4. I'm sorry, the predecessor of 5 is 2. So 2. And then I move to 2, and the predecessor of 2 is 1. So the shortest path is 1, 2, 5, 6 with a distance of 6. And that's the solution. As I mentioned already, you can also find the shortest path from the source node 1 to any other node. And also you can represent this network problem that we just discussed as an integer program. An integer program, as we discussed already, is a linear program in which some of or all of the variables are required to be integer. We formulate the shortest path problem as an integer program, and we find the shortest path from 1 to 6. So the decision variables are going to be xij equals 1 if arc ij is in the path, xij equals 0 if arc ij is not in the path. There is one arc out of node 1, and there is one arc out of node 6. For every other node I, the number of arcs on the path entering node I is the number of arcs leaving node I. Other constraints can be added, but this turns out to be enough. So by looking at this network again, we can set up this problem using those decision variables. And if you multiply those coefficients to each one of those variables, those are the constraints. So this is the constraint matrix in the no-arc incident matrix. So this concludes this lecture. So the questions, any questions, you can send me an email, or we can set up office hours, or we can meet during my office hours. So we discussed the notation and terminology, the shortest path problem, and the Dijkstra algorithm to solve the shortest path problem.